Today we're going to look at practice problem 2 from week 11. This one looking at energy, particularly when internal energy in a system changes because of friction. So first, let's read the problem. A water slide of length L has a vertical drop of H. Abby has a mass of M. An average friction force of magnitude F opposes her motion. She starts down the slide at initial speed VI. Use work energy ideas to develop an expression for her speed at the bottom of the slide. This one's a little bit different. We don't have numbers. We're being asked to find an expression. Particularly, we're looking for her final velocity. So as always, let's start by sketching our problem. So there's my slide. At the beginning of my initial moment, that is not how a person's head connects to their body. There we go. That is Maddie. She has a mass of M. There's a vertical drop of H. Let's just make that perfectly straight to make my life a little bit easier. Now in the final state, Maddie is down at the bottom. She now has a height of 0, so let's call that y1 is equal to h, y2 is equal to 0. The distance that Maddie has gone is L. That's what the length of the water slide tells us. And we're also told that there is friction. And that friction is being exerted on Maddie by the slide the entire way that she's going down. So I'm going to sort of draw a little bit of an intermediate step here where Maddie is moving downwards. All right. Her velocity here is v initial. Her velocity here is what we're trying to find. So here she's moving in the middle. She is also accelerating. But we are told that there is friction. Okay. So let's draw my representations. So first I can draw a motion diagram. So we are told that she is moving with some initial velocity VI. I think she's going to be speeding up. It's possible that she'll be slowing down because there is friction, but I think if that were the case, then she would stop halfway down, and that does not seem likely for a water slide. So here's her final velocity. Delta V is going to go in that direction. So this is my motion diagram. Let's draw a force diagram. Okay, so here's the surface of the slide. What are the forces that are exerted on Maddie? Well, so the object that my force diagram is being drawn for is Maddie. The objects interacting with her are the Earth and the slide. So this will be the force the Earth exerts on Maddie. And then the force the slide exerts, I know it's going to have some normal component and there's going to be some friction backwards. So I'm going to draw it somewhere in that general direction. I'm not sure exactly how far in each direction it's going to go. That's okay. So this is the force the slide exerts on Maddie. I can break that into its components. There's the normal component of the force the slide exerts on Maddie. And there is the friction. Okay. So from these representations so far, I can already tell that I don't want to solve this with forces and kinematics. I probably could, and as a means of evaluation, I could do it that way and make sure that I get the same answer. However, looking at my force diagram here, this is going to be gross. So maybe a different way of looking at the problem will make it a lot simpler. So now, let me also draw an energy bar chart. And let's see if that makes my life any easier. So my initial state is when Maddie's at the top of the slide. My final state is when she's at the bottom of the slide. My system is going to be Maddie and the Earth. And because there's friction, I'm going to add the surface exerting the friction. So I'm going to add the slide to my system. So now, let's think about what we've got. So we could have kinetic energy, we could have gravitational energy, we could have elastic energy, we could have work, and she could end with kinetic energy, she could end with gravitational energy, she could end with elastic energy, and there could be a change in internal energy. So now, let's figure out if we have any of these energies present in our system to begin with. So in the beginning, she is moving, she has some initial velocity VI, so I'm going to give her a box of kinetic energy. And maybe I'll change the number of boxes later on. Let me see. So now, does she have gravitational energy? Well, she does, because she has some height off the ground, and she's getting lower. So I know that her gravitational energy is the highest here that it's ever going to be. So let me give her like 3 boxes for that. There we go. Is there elastic energy in the system? Well, there's no spring, there's no rubber, there's nothing to be compressed or stretched, so no elastic energy. And is there work? Well, if I look at my force diagram, the only things exerting forces on Maddie are the Earth and the slide, and both of those are in my energy system. So no energy can come in from outside, so there's no work done. Now, in the end, kinetic energy. Well, I'm assuming that she's moving faster at the end than she is at the beginning. And that's the assumption I'm going to work with. If she's not, then my math will tell me somewhere along the way. So if that is the case, then her kinetic energy increased. I drew 1 box before. Let me draw 2 boxes now. Does she have gravitational energy? Well, I said her height at the bottom is 0. And if her height is 0, then she has no gravitational energy. And there is still nothing in the system that can store elastic energy. So now, let's look at my bar chart to see if internal energy should have increased. Well, there are a total of 1 plus 3. There are a total of 4 boxes in my initial state, but only 2 boxes accounted for in my final state. And I said there should be no work because there were no forces exerted by objects outside my system. So the total number of boxes of energy in my system should stay the same. So if there were 4 before, there should still be 4 now. So they should have gone to internal energy. That looks a little bit small for 2 boxes. Doesn't really matter, but it'll bother me. There we go. So according to my bar chart, the amount of internal energy should have increased. Now let me evaluate that for a second. Does it make sense? Let me make a little note that I'm doing an evaluation here. So I said delta U internal is greater than 0. Because I couldn't think of where else. Think of anywhere else. The energy went. But does it make sense? Does that make sense? So why would the internal energy be increasing in this problem? Well, I know there's friction. And when things rub together, they get warm. So I can say that, yes, friction increases internal energy. So notice that as I'm going, I'm evaluating whether the things that I'm writing make sense to me. So I found mathematically that there should be an increase in internal energy, but then I had to check, does that make sense in terms of the physics? Does it make sense that the internal energy would be increasing? And if there's friction, then yeah, it should be. So now, let me turn my bar chart into an equation. So I have 1 plus 3 is equal to 2 plus 2. So my kinetic energy beginning plus my gravitational energy at the beginning is equal to my kinetic energy at the end plus the change in internal energy. So that's the equation that I'm getting directly from my bar chart. Remember, this is part of why we draw bar charts, is to get an equation that we can then use to get more mathematical answers. So now, what am I looking for? So I am looking for an expression for the final velocity. So let me take this, let me take the equation that I came up with, and let me substitute in the equations for all the different kinds of energy. So kinetic energy is 1/2 mv squared. Gravitational energy is mg. Kinetic energy is once again 1/2 mg. 1/2 mv squared. And then the change in internal energy. So the only time we have an equation for the change in internal energy is when that change in internal energy is coming from friction. And that's exactly what we have here. So I can use that. So the change in internal energy due to friction is the force of friction times the distance along the surface the object moves. And the distance along the surface that Maddie moves is that length L. And so I'm looking for an expression for V2. So I want to isolate V2. So I'm going to subtract FL from both sides. So I get 1/2 mv1 squared plus mgy1 minus FL. It's equal to 1/2 mv2 squared. I can then multiply both sides by 2/m. And that will get me 2/m times 1/2, or 1/2 mv squared is going to be v1 squared plus 2 gy1, that mass is going to cancel with that mass, minus FL over 2FL over m. And that's just going to be v2 squared. And then this is going to square root all of that, square root of that, flip that around to make my life a little bit easier, and I get v2 is equal to the square root of v1 squared plus 2 times g times y1 minus 2FL over m. And this looks a little bit gross, but this is about what I get in terms of all of the quantities that I'm given. So this is the expression I get. So I was actually in the problem given two ways to evaluate this. So I was told to evaluate it using unit analysis and limiting case analysis. Let's talk about both of those. So I have an expression for velocity. So my unit analysis velocity is measured in meters per second. So when I look at the units of this entire thing, I should get meters per second. So let's take a look at that. So I have the square root of V1 is measured in meters per second squared plus 2 doesn't have a unit. The unit of G is newtons per kilogram. Units of Y is meters minus, again, 2 doesn't have units. The units of force is newtons. Units of length is meters divided by the units of mass is kilograms. So this is meters per second squared. A newton, I know, is a kilogram meter per second squared. So this is a kilogram times a meter divided by seconds squared divided by kilograms, all times meters minus kilograms times meters divided by seconds squared times meters divided by kilograms. All right. So this kilogram is going to cancel that kilogram. These two m's are going to multiply. This kilogram is going to cancel this kilogram. Those two m's are going to multiply. So we get the square root of meters per second squared plus meters squared per second squared minus meters squared per second squared. I suppose I could evaluate the meters per second squared and get meters squared per second squared. So all of these things that I am adding and subtracting have the same units. So when I add them all, I'll get that unit. So the square root of meters squared per second squared is meters per second. So unit evaluation checks out. So now the next thing that we're doing is limiting case analysis. So limiting case analysis is asking ourselves this question. Does our expression make sense for certain values? Of each quantity. So let me rewrite my expression. So we have V2 is equal to the square root of V1 squared plus this was 2GH. Oh, I realized I wrote this before. Y1 is actually giving us the problem as H. That'll simplify my life a little bit. Just less things to write down. Plus 2GH minus two times friction times the L over M. So that's my expression. So here's the first thing that I can immediately ask. What if there is no friction? So the limiting case here is the case where F is equal to 0. So how should that behave? Well, if there is no friction, all initial energy should become kinetic energy. There should not be an increase in eternal energy. Should become K2. So if I take my equation here and I just set the force equal to 0, so V2 is equal to the square root V1 squared plus 2GH minus 2FL over M, and I set F to 0, well, this last term is going to disappear, and I get V squared is equal to the square root V1 squared plus 2GH. And now let's look at this would be what this should be. So we said that all of the initial energy, so K1 plus UG1 is equal to K2. So 1/2 mv1 squared plus mg. I'm just going to use h here. Is equal to 1/2 mv2 squared. And I can solve this for v2, and I should get this. So I'm going to multiply both sides by 2 over m, 2 over m. I get v1 squared is equal to, or no, v2 squared plus 2gh is equal to v2 squared. v2 is equal to the square root of v1 squared plus 2gh. Notice that those agree with each other. So my expression behaves the way I think it should if there were no friction. So that's one limiting case that I can use. And there are others I could look at. So for example, I could look at how does this behave if the height is 0? And one thing that we have to remember when I do this. So what if h is equal to 0? And one important thing to remember is that my slide is a triangle. So if h is 0, then L must also be 0. I cannot set one of those to 0 without setting the other. So let me actually say, so what if h equals L equals 0? So what should happen to my speed if there is no slide? Well, I think the obvious case here is that v2 should equal v1. I will say should here. So should equal v1. Does that make sense? If there is no slide, then my final velocity should equal my initial velocity. So v2 is equal to square root of v1 squared plus 2gh minus 2fl over m. I am setting this term to 0 and this term to 0. v2 is equal to the square root of v1 squared. v2 is equal to v1. So that's another way where this equation behaves the way I expect it to if I set things to 0. So the two most common limiting case analyses that we do are set a value to 0 or set a value to infinity. And here we set both of them to 0. It doesn't really make sense to set anything to infinity here. Like maybe we could make the slide infinitely long, but we know that if the slide is infinitely long because there's friction, Maddie is not going to go along the entire thing. She's going to stop eventually. So setting L to infinite doesn't really matter for us. And that would be changing the physics, not just thinking about the situation. So I think that we've done enough. We've shown that the units work, and we've shown that our expression behaves the way we expect it to if we remove friction, and it behaves the way we expect it to if we remove the slide, if we set the height equal to 0. So I'm convinced. So this expression behaves the way I expect it to. So I will just rewrite my final answer, v1 squared plus 2GH minus 2FL over M. And one thing that I want to point out, notice that this term and this term do not depend on Maddie's mass at all. But this last term does. Or it looks like it does. But in reality it doesn't, because one thing to keep in mind is that hidden inside of here is that friction depends on mass. So really the dependence of friction on mass and the dependence of the mass down here, those will cancel it out. So V2 does not depend on Maddie's mass, even with the friction, because the friction will be twice as large if Maddie is twice as massive, and then it will be divided by a mass that's twice as large, and those two will cancel each other out. So that was just something that I thought I'd mention while we're here. All right, thanks for watching.